Welcome to a session on principle and structure of an optical fiber. Definition of optical fiber. An optical fiber is a cylindrical waveguide made of transparent dielectric material. It may be a glass or it may be a plastic, which guides light waves along its length by total internal reflection. This is called as optical fiber. Let us discuss the principle behind the working of optical fiber. The propagation of light in an optical fiber is based on the principle of total internal reflection. Conditions for total internal reflection. Light should be passed from denser medium to rarer medium only. The angle of incidence in the denser medium should be greater than the critical angle. So this later we will verify in the next section. Let us see the structure of optical fiber. It has three coaxial regions, that is core, cladding and buffer jacket or outer jacket. Let us discuss one by one. First one is core. It is the innermost cylindrical region. This yellow one is called as core. It is also the light guiding region. So out of core and cladding, core has more refractive index, which means it is a denser medium. It is made up of with denser medium and compared to cladding. Actually, light is passed through this core medium only. Next one is cladding. The core is surrounded by the cladding. So this cladding region is surrounded by this particular core. So the purpose of cladding is to maintain a rarer medium. So to satisfy the condition of total internal reflection, core is a higher refractive index region and the cladding is a lower refractive index region. Next one is outer jacket. The whole and sole purpose of the outer jacket is to give mechanical strength for the core and cladding. Next, let us see the total internal reflection mathematically. So let us consider there are two regions. This region, somewhat yellowish region, is called as N1. So whose refractive index is high? Let us consider the another medium whose refractive index is N2. Of course, N1 is greater than N2, which means the refractive index of this yellow region is more when compared to this N2 region. Let us consider theta 1 less than theta c in this particular case. So here I am incidenting a light ray in the denser medium with an angle of incidence theta 1, which is very less. In this case, what happens is the light ray refracts from first medium to second medium, and this is the theta 2 is the angle of refraction. Now let us see the another case when the angle of incidence in the denser medium is equals to the critical angle. So now here this particular light ray making an angle theta 1. Of course, from the figure it is very clear that compared to this theta 1, this theta 1 is more. So more angle of incidence is there. So if this theta 1 is equals to critical angle, then what happens, this light ray refracts along the boundary between the two mediums, N1 and whose refractive indices are N1 and N2. So this is one medium, this is one medium. The light ray travels along the boundary line between the two mediums. So here angle of refraction is 90 degrees. Here if you measure theta 2, it is 90 degrees. The same here it is represented. If theta 1 angle of incidence equals to the critical angle, then the angle of refraction theta 2 equal to 90 degrees. Now let us concentrate on figure C. So here when theta 1 greater than theta C, here the angle of incidence theta 1 is greater than the critical angle. In this case, what happens is the light totally reflect back to the same medium. This process is called as total internal reflection. The light totally reflected back to the same medium. Here the condition is angle of incidence should be greater than the critical angle. So this is one condition. The second condition is the light should travel in denser medium and it has to hit the rarer medium. Then it totally reflects back to the same medium. This is called as total internal reflection principle. The propagation of light in an optical fiber is based on the principle of total internal reflection. Condition for total internal reflection. The refractive index of the core material N1 must be slightly greater than that of the cladding material N2. So, this is core medium. This colored region is core medium. This is cladding medium. So, what we are stressing is this core have high refractive index when compared to cladding. Then only total internal reflection will take place like this. If the angle of incidence here in this denser medium is greater than critical angle, now this light ray totally reflects back to the same medium. Snell's law. So if we apply Snell's law, it becomes n1 sin theta 1 equal to n2 sin theta 2. Here theta 1 is the angle of incidence, theta 2 is the angle of reflection. N1 is the refractive index of the first medium, N2 is the refractive index of the second medium. Generally, N1 is the refractive index of core and N2 is the refractive index of cladding. If we take the condition theta 1 equal to theta c, when angle of incidence equals to critical angle, at that case we have seen that theta 2 angle of reflection equal to 90 degrees. So by substituting this in Snell's law, so n1 sin theta 1. If you substitute theta 1 equal to theta c, then the equation turned like this. n2 sin theta 2. We chosen theta 2 as 90 degrees, sin 90. We know sin 90 equal to 1. So n1 sin theta c equal to n2. From this we can write sin theta c equal to n2 by n1 or theta c equal to sin inverse of n2 by n1. So we can find out the critical angle between the two mediums by using the formula theta c equal to sin inverse of n2 by n1. Only we have to know n1 and n2, refractive index of the core, refractive index of the cladding, or refractive index of the denser medium, and the refractive index of the rarer medium. Thanks for watching. This is the structure and principle behind